For this video, I'm going to show you what gradient descent with momentum looks like in 3 dimensions and how it compares to gradient descent in general. We're going to look at a couple of functions for this. I'm going to show you some visualizations and then we're going to code this all together. I'm going to show you how I coded this. And what you're going to see is you're going to see that gradient descent with momentum will allow you in some circumstances to bypass a local minima to reach a global minima or a more ideal minimum. Now, this is something that gradient descent just by itself won't allow you to do. And note that I did do a video on gradient descent with momentum in 2 dimensions. So I'd recommend watching that first if you want a better overview of the topic or if you're new to the concept. Anyways, let's get started. So the function that we're looking at first is going to be sine x times cosine y. Don't worry too much about the code for now because we'll get into that later on. But let me show you the visualizations first. Alright, so here we have the plots. They are the same graph, by the way, and the minimum is where my cursor is here and then here. And both the algorithms start in the same place. So each iteration shows the new position of the black bowl, you could say. We see that with gradient descent, it's a lot faster at first, and then gradient descent with momentum is a lot slower at first. You see each of these points are very closely packed together. Now the reason for this is that the term corresponding with the gradient, for gradient descent, is going to be larger because what's multiplying the gradient in gradient descent, or the slope, the derivative essentially, is lambda. What's multiplying that term in gradient descent with momentum is lambda times 1 minus beta. Now 1 minus beta is going to be less than 1, and it's actually potentially and probably going to be quite less than 1, so maybe like 0.2, 0.1, because usually beta is 0.9 or even 0.99 or above that. So it starts off small because it doesn't actually have any momentum at first, because there's another term. I'm not sure if you're familiar with the equations for gradient descent with momentum. If not, then I'd recommend either watching my previous video or just Googling the equations beforehand. But there's the other term that consists of the momentum. And at first, that really doesn't account for much. So that's why it starts off slow. But then as it picks up the momentum, then that term accounts for more. And even though the term consisting of the gradient isn't as large as for gradient descent, the term for the momentum makes up for that. So that's why it actually picks up speed down here. Yeah, and what we see is that with gradient descent, it goes pretty much straight to the minima here. But with momentum, because it's got that momentum, it actually looks more like a bowl rolling down a hill. So it goes down here and then it kind of spirals here and it'll settle in the minimum. So now it's not really moving much because there's not much momentum, and the gradient is close to 0 as well. But what you'll see is it'll kind of spiral here and settle in this minimum. Anyways, I won't let it do that too much because it will take a while, but that is for one function. And you can see that gradient descent with momentum wasn't too useful there, but we're going to look at a function where it is useful. Just bear with me, I'm going to change around some parameters here. And now this function is called the Ackley function. This one here, z is equal to all this stuff. It's a common function that's used with testing optimization techniques. It was proposed by a guy named David Ackley. What I'm going to do is actually include some stuff in the description if you're interested to check it out. It's actually quite interesting looking at these, and there's a bunch of other optimization sort of functions that are used to test these techniques. And the derivative is kind of crazy actually, but I didn't do it by hand. I just went on Symbolab and typed it in and it came up with this, so that's good. Okay. That should be everything, I think. Actually, hang on. This should be... I'm going to change this lambda here just because it's easier to compare the two algorithms in this function with this specific lambda number, 0.019. Okay. So these are two different views of the same function, but one is with gradient descent and the other is gradient descent with momentum. And you can see the bowl here. This is gradient descent. These are all local minima around here. Well, and this is the global minima. It's also the local minima at that place, but it's the global minima. It's the most ideal solution that we want. So we want the algorithm to converge there. And this is the same place on the plot in the different view. What we see is with gradient descent, it starts here and then it goes down to this minima, which is not the ideal minima, but then it stops there because there's no momentum to carry it forward. But with momentum, on the other hand, it starts in the same position and it starts off slower, as explained earlier, but picks up the speed, and then that momentum is enough to actually carry it over this hill here. And then it'll actually be able to get to this ideal minimum. And what it will do is it won't actually just stop there. It'll go up a little bit. Like imagine a bowl rolling down a hill. It'll go up and then it will kind of settle down in this minimum. So in this situation, we see that the momentum aspect actually allowed gradient descent to reach a more ideal solution. See that there's more dots here, it's getting thicker, which means that it's kind of settling down here. But anyways, that's the visualization section, and now I'm going to get to the coding section. See you there. Alright, here we are going to get to the coding section of gradient descent with momentum in 3D. I just realized I forgot to add a dot py at the end of this. There we go. Alright, so I'm going to show you basically how to code everything that you saw in the visualization section. So firstly, we're going to import matplotlib. We're going to import numpy. Alright, what do we need? We need the function first off, and this is going to be a three-dimensional function, so it's going to take in an x and a y, and it's going to output a z. So we just define it here. We call it f of x and y, and we can start with the function that we showed in the visualization, which is cosine times what was it? No, sine of x times cosine of y. Yeah, like that. And if x and y are scalars, z will be a scalar, but this will also work for if x and y are arrays. So when we actually plot the surface at first, this will work as well. We can use the same function. And we need the derivative as well. And the derivative is, what is it? With respect to x, that is cosine of x times cosine of y, I think. Is it? Yeah, it is. And then with respect to y, that is sine of x times negative sine of y. Just looking over it. I think it is though. X and then negative sine. Yeah, of course it is. And then we return both of these. Alright, we have the functions for the actual function, and then we have the derivative. So now what we're going to do is we're going to create gradient descent and then gradient descent with momentum as separate functions, and then these are going to be called from a comparison function which will plot both of them side by side as you saw in the visualization. So we can do gradient descent with first because that's a little bit easier. And we pass in x initial, y initial, which are going to be the initial values for x and y. And for I in, wait, no, that's not it. we're just doing one iteration here because we're going to actually do the for loop within the comparison function. So that is, actually we don't need x initial, y initial, we just need x and y. X is equal to x minus lambda times grad x. Yep. So these are just the update formulas for gradient descent. Or instead of grad x, we can write dfx and then dfy. Like that. So we need to define a lambda, but we also need dfx and dfy. Or even better, we can do this within the function. We can say dfx, dfy is equal to dfx and y, like that. That way there's less arguments here. Just looking over it, but I think that's fine. Yep, and we return x and y, which are the new updated values. And that is everything we need for gradient descent. Now we need gradient descent with momentum. And I don't really remember what it takes in at first. I know it takes in beta. What we can do is we can actually pass this in the argument, and then when we call it, we can pass in the value for lambda and beta. I think that'll be better. So lambda, beta, it needs x, y, dfx, dfy, and vx and vy. Yep. Wait, no, it doesn't need these because we're going to calculate those. So dfx, dfy, this is the same as we did in gradient descent. This is just to calculate the derivatives. And vx is, what is it? Beta times vx plus 1 minus beta times dfx. Yeah, that's it. And we do the same for y. So these are just the equations for gradient descent with momentum. Well, these are the ones that I like to use. There's different ones, like I explained this before, but you can take away the 1 minus beta, and there's just different ways to do it, but I do it this way. So yeah, we calculated this for that. And then we go x is x minus lambda times Vx. I'm doing this off the top of my head, but I'm pretty sure this is what it was. We'll find out. If it doesn't work, then, well, we know something's wrong. But I'm pretty sure this was it, yeah. X is x minus lambda times Vx. Alright, that'll be everything we need. And we don't only need to return x and y, the new updated values, but we need to return the new values of Vx and Vy because they're going to be used in the next iteration. Alright, those are all the those functions that we need anyways, but now we need to create the loop, or the function that calls the loop for gradient descent and gradient descent with momentum, and that'll also plot the whole iterations. So we can just call it, I don't know, what do we call it? Comparing gradient descent with momentum. All right, what do we have? We firstly need to create the figure. So that's plt.figure. And then we add the subplots. So we have 2 axes for those. And this is just, what I'm writing now is just organizing the figures, you know, the plots. So we do gradient descent at first, and that's a subplot. Add subplot, and we can call it 1, 1, 1. And it'll be a 3D subplot. So 3D, like that. And GDM, that'll mean gradient descent with momentum. And that'll be, what did I think I had this before. I don't know if it matters. I've always just really seen 1, 2. So I'm going to do that. Projection is the same 3 dimensions. You can also set the titles. Oh no, it's not dot equals set title, it's dot set title. And that's gradient descent. And then the other one is with momentum. Like that. All right. So now we need to actually create the surface at first. So the plot of the surface, which is going to include, which is going to be of a mesh grid. And we need to actually define the mesh grid, but we need to define the values for the x values and the y values. So I'm just trying to remember how I did this, but I think it was x values is a range. Yeah, I think it was a range. X values, y values is np.a range, and that is from, let's say, -2 to 2 and step size of 0.1. And that'll be the same, like that. So that's going to create a array, and it's going to be all the values from -2 through to 2 with step sizes of 0.1. So it's going to be -2, -1.9, -1.8, and so on. So then we can create the mesh grid for that. And a mesh grid is a way to plot in 3 dimensions. And what you'll see is it'll create every sort of combination. So let's say that you have a mesh grid of the values 1 through to 3. So that'll create 2 arrays, x and y. And x is going to be 1, 2, 3, 1, 2, 3, 1, 2, 3. And y is going to be 1, 1, 1, 2, 2, 2, 3, 3, 3. And if you combine those 2 arrays, you can imagine that you have every sort of possibility, every combination between x and y. And that's a way to plot in 3 dimensions, because you need to have every combination between x and y. Because you can imagine the x and y axes, that makes a square, which means that you need every combination between the x-axis and the y-axis. And then you just calculate z for all those combinations, and you can plot the surface. So NumPy does have a function with that, and it's called mesh grid. And I believe it just takes in x values and y values like that. And then we plot the surface. So that is, we plot it on both of the plots, because we need to plot the surface on the gradient descent one and the gradient descent with momentum one. Yep. So I think it's a plot surface. It's not coming up, but I'm pretty sure it is. And we plot x, y, and then f of x and y. So remember, f is the function. So when it takes in x and y, it will put out a, what is it? Here it is. So x can be either a scalar or an array. In this case, x is an array and y is an array as well. So z is going to be an array. So z is going to be in the same size as x and y. X and y are in the same size as well. So z is going to be the function at every combination of x values and y values. And then we need a color map, which is basically the way that the colors are presented in on the surface. And is it Cividus? Cividus. Got it written down here, Cividus. That's the one I was using. And then we can define a parameter for, or an argument for alpha. Alpha is the transparency of it. So the lower it is, the more transparent. And alpha is maxed at 1. So you put in a value between 0 and 1. I like 0.7. That's a little bit transparent, which is good, because then you can see the bowl kind of rolling. And then we plot the surface for this one as well. And we can use the same values here. Civitas, and then alpha is 0.7. We'll pause it for a bit. And what that'll do is that'll allow the person that opens it up to just see the plot first before anything is happening. So we'll just pause it for I think it's in seconds. But that just allows an animation to take place. And then we just scatter the initial point. So we need to actually define the initial point. And we'll put it in here as well. Now the initial values are, let's set it equal to, I don't know, 1.50. I think off the top of my head, that's what I had in the visualization, but we'll see, because yeah, we need a point where it's kind of on the top of a hill, because otherwise it won't really show much, but we can kind of change that up once we actually plot it. So let's just plot this for now. So we can say PLT, ax GD, because we're plotting it on both of the subplots. So we go scatter, and that'll be, so we're passing in the initial values, and then we're gonna calculate f at those initial values. Yeah, and we do the same for GDM. I believe that's the same value, yeah. And then we can pause for another 2 seconds just so the person can see where the bowl is and kind of take in the environment before we start anything else. And now we do the loop, which is the iterations. So we create a for loop and we run it for a certain number of iterations, and with every iteration we update x and y for both of these, and then we plot them. So let's say for I in range, 50 iterations. All right, how do we do this? So we need to create two sort of variables for x and y. One of them will just be x and y, or one pair will just be x and y, and that'll show the iterations for gradient descent. And then we'll do the same for x underscore m and y underscore m, which will show x and y for gradient descent with momentum. And that way we can just plot them separately and it will be a little bit easier. So I'll show you what I mean. X and y is gradient descent. And what do we pass in? We pass in x, y, and lambda. So lambda is, let's just set it to 0.1. Yep. And then we go, oh, did I just run it? I think I just ran it. Okay, and then x, m, y, m, vx, and vy. And what these are the values for the momentum. So I've just put the underscore m to differentiate between the two. So that's gradient descent with momentum, and that takes in xy. Let's just call these xm and ym. And we'll do the same here. Just for completeness there. Okay, so we pass in xm, ym, vx, vy, and what else is that? Lambda and beta. Lambda is 0.1, beta we'll set to 0.9. And we actually need to define these values here, so we can define xm, ym is, well, hang on, what do we have? Firstly, we define x and y, so that's x initial, y initial. And then we define xm and ym, which are going to start at the same points. And then we need to define the first values for vx and vy, which are going to be just 0, like that. Yeah, because these values here for the momentum case, they always start at 0. That's their initial setting. And then these other values, they just start at whatever x and y start at, which is x initial, y initial. So these two functions here, what we've done is we've passed in whatever we need for the algorithms, for the two algorithms, and we have updated the values. So now we have a new x and y, and now we have a new xm and ym in one iteration, and then we have these values which will get passed into the subsequent iteration for the momentum case. So we actually need to plot this now, and we can do it like this: xgd dot scatter xy f of xy. So this is just plotting for the gradient descent case, the new updated xy value, and then the function at that value, and xgdm. So this is the gradient descent with momentum case. So instead we pass in the momentum x and y, and then f at those values. And we want to pause for, let's say, 0.3 seconds. So this 0.3 second, what that's referring to is the pause between each bowl change. So if you remember on the visualization section, the bowl didn't disappear. So it wasn't actually, I didn't make it kind of like a bowl rolling down a hill, meaning that I kept all the previous iterations, so that you could kind of see what's going on and the general trend of it. So this 0.3 refers to the time between each change of the black point. So these two are just before so this one is after the surface plot appears, so that the user can kind of see the situation first. And then this one is after the bowl first appears, so the first initial point. And this one, if we put it 2 seconds, it will just take too long between each iteration. So that's why it's 0.3. It's just a little bit faster. I think that's it actually. Let me just think. So we just finished with plt.show, and I believe this will be it. So let's try it out, and hopefully it works out the same way. So x initial, y initial, and well, x values, y values are defined up here. So for completeness, what we can write is actually x values, y values, just in case you have different variable names. That's just better form for functions. In general, what else we have? X values, y values. We don't have any other variables, I don't think. X values, y values. What we can actually define is lambda. So lambda is equal, that's going to be a function. Lam is equal to lambda, and beta is equal to beta. And we can put in here lam. We can put in here lam and beta. And then lam beta. And then we can define these up here actually. That's just better form, so that we don't have to actually change much in the function. If we're changing the values, we just change the arguments that we're passing in. And also, just for completeness. Oh no. What did I do? Oh no. There we go. I think that's everything. Just going to go over a little bit. Lam beta. Oh, and these are x, m, and ym. The reason I'm doing it like this and not just going off, like I've got notes to the side of me, but I prefer to actually code it by kind of thinking what I'm doing rather than just copying directly from my notes, because I think that just makes for a better video, because you can kind of see more my thought patterns and what goes into writing this code rather than just me copying directly from my notes. All right, let's test it out and we'll see if it works. All right, that's good so far. So we can see the bowl started up here. can't really see the ball very well, and that is because of a parameter that we can change, and that is called the z order, which we write over here. So the z order basically tells what is a priority in showing, like when you show a plot and you have two different sorts of plots, like maybe you have scatter plots and then just a surface plot in the same axis, then you kind of want to tell matplotlib which one's more a priority, and what it will do is it will kind of like show that one above the other one so that you can see it better. So if we put z order of, not 1, 0 here, order of 0, and when we plot the scatter points, we want to put a z order of 1. And what that's saying is that's saying that we want to prioritize the scatter points, so they should appear with better on the screen. I'm not explaining that the best, but you'll see when we see the plot that they will appear more vividly on the screen compared to the surface plot. Actually, what I will do is I will copy this part from my notes and initialize a view. And a view is basically what view of the plots we see when we first open it. And that way you can kind of set it so that it shows at a view that shows what's happening, you know? So view init, that's what we do. And there's certain parameters here that we can put in. And how to find these parameters is when you actually just move the plot around with your mouse, these parameters appear on the top right, I believe, of the screen. So once you find a view that you want to see, then, so 119? Yeah, 119. Once you find a view that is ideal, you just look at the parameters on the top right and then you just put them into this view init function. All right, let's run it. All right, there you go. So you can see the ball a little bit more clearer now. Oh, I didn't set the color for it, so the color is going to change with every iteration. That's fine. You can still see it moving. It looks like it's doing what it's meant to. Of course, it's going to take a lot of iterations to get down, especially the one with gradient and with momentum. So I might actually pause. Oh, yeah, because we didn't have enough iterations. Of course. All right. Firstly, what we can do is actually set a color for this. So C is black. The 0 it means black, and then the C means color. So we set that. We increase the iterations, say 150, and we pause for not much at all. That way it'll go faster. Anyways, I'll skip it to where it finishes up. All right, it looks like it's gone through. Now, the one with momentum actually looks very similar to the one with gradient descent. I feel like maybe I plotted the same graph. Maybe. Oh wait, hang on. Y value, is that an issue? Maybe that's not an issue, but did I plot the same graph? Alright, so the plot that I showed just then didn't really demonstrate the situation very well. And I was like wondering maybe I coded something incorrectly there, but I had a look at the previous code, which is the one that I showed in the visualization, and I'm thinking it might just be because of the initial values. So I set the initial values to the same that I did here. Anyways, we're gonna start the code with this X initial and Y initial. So I'll run it and then I'll edit out the part where it's taking a while, and then I'll show you the end and we'll see if it's we'll see what it comes out with. There you go. So yeah, we get the same situation that we saw in the video. So yeah, the previous plot just had, maybe it was just the starting position that didn't really highlight much of a difference. Like with gradient descent with momentum, you saw that it went down differently than gradient descent, but it didn't show this spiral situation, which is just because of where it started. But this one highlights the difference. So you can see that they both start in the same position. Gradient descent goes down a lot quicker. You can see that because the points are more far apart. But then gradient descent with momentum, it has this curvy, it has this spiral situation going on at the end, which is because the momentum is actually carrying it around like this. And it's going to take a while before it gets back down to this position here because the iterations are very close together at this point. Alright, well that is how to code gradient descent and gradient descent with momentum. The code that I showed here is a little bit different than the one that was in the visualization. So if I'm just going to scroll down this in case you want to compare the codes, but they do the same thing. For example, I had this plotting adjustment thing here, and that is because when you plot the points on the 3D graphs, they appear half above and half below the surface, because you can imagine that the very center of the points is going to be the point where they are on the graph. So the plotting adjustment, I was experimenting with this and just set it to maybe 0.03 just to make the bowl appear above the surface, so it actually looks like it's rolling down the surface rather than rolling through the surface. But in the end, I think with the video I just left it at 0. What else is there? Oh yeah, I put this marker thing here for the other code, but I think that just is a standard marker. That's just like a bowl. I think that's pretty much all the differences between the two codes. Anyways, I hope that helped. That was gradient descent with momentum in 3D. And I reckon I might actually do a video in dimensions after 3D. It's going to be hard to visualize that because I don't know how to plot a graph in 4D, but I'll experiment around and hopefully I'll be able to create something that can make it visualized, that can visualize gradient descent with momentum for you in dimensions after 3. And if I do, then I will make a video on it. Thank you for watching.